I will go ahead and introduce this webinar event for today. So this is our last installment of an ongoing series that we've had for the International Year of Quantum. So today we're going to be talking about the future of high energy particles. So in this seminar, the topic kind of in a broader sense is how we look at the world of high energy and particle physics, particularly examining how quantum theories are unlocking the mysteries of the universe at the smallest scales. So a little bit of background about this series. So APS, in partnership with the Johns Hopkins Science Diplomacy Hub, welcomes you to an innovative international event dedicated to advancing global collaboration and understanding in quantum science and technology. This is one of several worldwide initiatives to celebrate 2025 as the International Year of Quantum Science and Technology. Our experience helps connect scientific communities, industry leaders, policymakers, national labs, and the public, fostering discussions on the transformative impact of quantum technologies. All previous webinars from this series can be found on the APS YouTube channel. Today, this is the final Quantum Connect webinar in the series, and we are joined by Kristin Beck, José Enrique García Ramos, Edward Witten, Michael Dozer, and Andreas Jung. So it looks like we have all of our speakers here today. So with 5 of us, it'll be a very exciting discussion. To begin with, I think we're going to give all of our speakers a chance to introduce themselves and tell us a little bit about what you do in the quantum industry, particularly with respect to how, we're talking about high energy particles and quantum physics. So whoever would like to begin can jump right in.
Okay, I can go first. I wasn't sure whether I should go, whether I think I'm the youngest, or no, I'm maybe not the youngest. Okay, so I'm a high-energy physicist by training. I moved from collisions in electron protons over to proton antiproton, and now at the Large Hadron Collider at the CMS experiment over in Europe. So that's part of the work that I do. So I did some first observation of quantum entanglement at the scales of the LHC energies, which is something very exciting for us. It's it's not really a new field, it's all quantum mechanics. But for us, it is the rediscovery, let's say, of quantum information science language together folded with high energy physics. And yeah, my group, my postdocs and students, so they have been working on the first observation of that at the CMS detector. And then more directly, which maybe is what you are after here as well, is more in terms of technology or actually using quantum computers. So that started about in 2018. I used, or my group used some D-Wave machines. At the time, they were really desperate for applications. So they gave out computing time for free, which is very different from today. Nowadays, you have to pay for everything with very high dollar amounts, which is a pity a bit. But at the time it was free, so we did some vertexing, event reconstruction with tracks. That's still some of my interest for the ongoing research. And then on the other side, I do supply chain and actually, solving really today's problem with quantum machining and quantum machine learning, AI, hybrid technologies, mostly on IBM-Q and D-Wave. I stop here. I don't want to take too much time, so let others introduce themselves, right?
Well, I can describe myself. My name is José Enrique. I'm from the University of Huelva in southwest Spain. And my background is essentially in nuclear physics. So this webinar is focused on high energy. So let's consider nuclear physics high energy, but it's not the case. But okay, let's go on. As I said, my background is nuclear physics, mainly working on algebraic method. And for some time, I was also interested in the so-called quantum phase transition and excited state quantum phase transitions in nuclear physics, but also in other model of interest in solid state physics and optics and indeed in quantum computing too. And Very recently, let's say 4 years ago or so, I started being interested in quantum computing, and indeed I start implementing a simple nuclear physics model, essentially a schematic nuclear physics model in quantum computers. And indeed, we manage to define a kind of observable with which we can indeed characterize the shape of the nucleus. And I hope that I will give you some interesting ideas about this during the webinar.
I can go next if Kristin or Ed don't want to go. All right. So I'm Michael Dozer. I'm a research physicist, particle physicist at CERN. And I started out being a high energy physicist, but since about 25 years have moved into atomic physics, and in particular anti-atomic physics, with atoms containing antiprotons or positrons. And since 4 years have been working on trying to define how best to bring quantum sensors into high energy physics or particle physics more generally contexts. And since last year, I'm leading a worldwide collaboration of 115 institutes that are carrying out R&D on quantum sensors for particle physics, where we're looking into a wide range of quantum technologies, covering atomic physics, covering quantum dots, superconducting devices, nitrogen vacancy diamonds for spin and polarization, entanglement, and so on, and trying to see where those can start playing a role in particle physics detectors in the future.
Um, I'm Edward Witten at the Institute for Advanced Study in Princeton. I don't really work on quantum technology, but since the world is quantum mechanical, all my work has involved quantum mechanics. Much of my career has been devoted to studying properties of quantum field theories that describe the elementary particles, and the rest has been trying to understand string theory, which uses quantum field theory in new ways, trying to include gravity in the picture. Although what has gotten me interested in quantum information science is actually the discoveries made mostly in recent years, but some of them have older roots, about how gravity uh, seems to, unlike other theories, gravity seems to know that it's going to be quantized. The first hint of this was the discovery by Beck and Hawking of the entropy of a black hole, the fact that area, a geometrical feature of the world, measures an entropy. And recent research in the last 10, 15 years has given many more indications that somehow classical gravity knows that it's going to be quantized. It's a complete mystery, so we don't know what to make of it. So I certainly can't tell you an answer. But that's what's fascinating me at the moment.
So I'm Kristin Beck. I'm an atomic molecular and optical experimental physicist by training. And I'm currently a staff scientist at Lawrence Livermore National Laboratory, where I head our virtual department on quantum information science, which connects our scientists all around the Livermore site who are interested in applying and developing the tools of quantum information science to meet whatever their scientific goals are. I'm also not entirely sure how I ended up on a panel for high energy physics. The last time I was really working in high energy physics was as an undergraduate summer intern working at CERN about 17 years ago, when I was looking at tracking cosmic ray muons through the CMS detector, which at the time was being gotten ready for the science missions that eventually helped us find the Higgs during what we called the Crusade campaigns. The closest part of my current my current research to high energy physics has been looking at the impacts of cosmic ray muons on superconducting qubits, looking at conditional effects on some of the decoherence times like T1 and T2 decoherence times on these qubits as an understanding of fundamental error processes for large quantum processing units.
Well, I think we're just happy to have you all. And it doesn't, what the degree to which your particular expertise connects to each other or to a specific topic is less important than what you have to offer, I think. So we're very happy to have you all on this panel. Um, so our first question for you all is, what was your quantum moment? So some experience that first really sparked your interest in quantum technologies and quantum sciences and set you on your current career path.
Can go first again, although maybe that's okay. I'll just
Go
go
right
ahead.
ahead.
And then next time we mix it up a little. So for me that was what I already started at least to say in a sentence in the beginning, that 2018 somehow realized that quantum annealing, or in general quantum computing platforms, can actually be used to solve something, right? Before it was mostly simulating algorithms or very theoretical work, which I'm not a theorist, I'm an experimental physicist. So it was about developing new algorithms that are better, or solving NP-hard problems and whatnot. So that I was not involved in that. But 2018, when it started to be, yeah, there's actually a number of qubits now that you can do something. Or on these annealing platforms, you had the corresponding thing of qubits, which you can use to solve. So for me, that was this great moment where then I don't know, for me it connected back to these old pictures from the 50s or 60s of these room filling computers at the time, right, that were not even a cell phone today. And so there's a start of a very exciting technology, maybe able to solve really large problems, computing wise. When that will be, I don't dare making any suggestions, right? Because that we are in this noisy time. But then still, for me, yeah, we have seen some improvements. So that was great. And that then quickly started on to see these quantum information science measurements, let's say, for the Large Hadron Collider, which is something I find truly exciting in all the wealth that it speaks. It also gets us out again out of our comfort zone and speaking with each other about quantum information science between different areas, which we have not done maybe before to that same extent. That was
In
for
Well, in my case, I should say that I entered into the field just by chance. A new colleague came to our department, and then just in order to start collaborating with him, we started discussing. He is an expert in really in quantum computing from the theoretical side. And then we said, okay, how can we collaborate? In my case, coming from nuclear physics, and then how can we really match and to create a kind of project? And in that case, we say, why not to implement one of our nuclear model into a quantum computer, a simulator at that time? And even with our simple model, we notice that it still is too complicated, and indeed we have to really to lower our kind of model and really to use almost let's say toy model, but model that are used indeed everywhere in quantum mechanics as the Lipkin model. And then we manage how to implement that. That's what one of the main or the first model that was implemented in a quantum computer regarding nuclear physics indeed. And then we did that step forward, and then we move into another simple model called the Agassi model, and indeed we manage, and really for me was really a discover in the sense that of course it's quantum mechanics. I mean, it's essentially normal quantum mechanics, let's say, but really the language changed a little. Also, to you start using these quantum information ideas that once more is just quantum mechanics, but really open somehow your mind.
So in my case, it was very simple. It was when I was a kid, reading a Scientific American article on neutron interferometry in silicon three-lobed crystal to measure gravity, and that sort of blew my mind. And I wanted to do something like that with antimatter for my whole life, and I will never succeed in doing that. But most recently, it was 4 years ago when I was asked to participate in writing a roadmap for bringing quantum sensors into particle physics, where I realized the breadth and the depth of the possibilities.
I would say that in my life, there have been two events that might be called quantum
So,
moments, but neither of them is a perfect match for the question. The first was in 1982, when I learned about the work of John Schwartz and Michael Green, showing how some of the problems with quantum gravity are resolved in string theory. That was highly illuminating. It certainly was a quantum moment for me. And the second one is harder to date, and I already kind of talked about it, but it happened when I became aware of all the hints discovered by other researchers, I should stress, that that Einstein's theory knows that it's going to be quantized. I have one more comment. In the logo of this, in the logo on our Zoom page, I apologize, I'm struggling with a cold, which you might be hearing. In the logo here, I see a knot. And I don't know if that's meant to suggest the idea of topological quantum computing. And that might even be why I was invited to this panel, although I have no idea.
I think that's partially the inspiration, yes.
Okay, so in 1988, I actually did do some work using quantum mechanics to develop invariants of knots. I was mainly trying to understand problems in conformal field theory that had been identified by colleagues, such as Eric Verlinde, and I had no thought at all that it would ever be used for quantum computing. That was proposed years later by people like Alexei Kitaev and others. But anyway, I think that was a fun moment in my career, but I can't quite call it a quantum moment in the sense that you're asking for it, because I had no idea of the applications to quantum technology.
So I can point back quite a long way. I'd always been fascinated by the world of the very, very small. And I think the first time that that really intersected quantum, well, more quantum mechanics than quantum information sciences at that time, was in understanding how we can measure time with atoms. So I spent a summer working with the group at NIST in Boulder that is developing neutral atom atomic clocks. And just understanding how, in this case, not the allowed and non-dipole allowed transitions in atoms can be used as very, very precise oscillators, was something that gave me a real fascination for how atoms act differently than the way that the world around us in the classical world tends to work. And that really was cemented for me as there are two different instances where I've been able to actually visit experiments, one that was a sodium experiment at Georgia Tech and another one that was um, an experiment that was using barium ions at the University of Maryland, where I was able to first see a cloud of atoms and then a single ion with my bare eye through a microscope objective going into a vacuum chamber. And that really solidified this, like, oh my goodness, I can actually use the sensors that I've been given as a human to see quantum phenomena that this really made me certain that this was the field that I wanted to be in and spend my life in, because there's so much really, really cool stuff that is just on the we know it's the world around us, but at the same time it's totally different than the way that our minds are used to seeing the world behave.
Yeah, wonderful answers from everybody. So our next question is, how has the landscape of quantum technology evolved since you began your career? And what developments have maybe surprised you the most?
I I will just stick to it, right? Then we know when to talk. If that's me. Okay, so for me, that was, I think certainly that there is also this exponential rise, let's say, in terms of qubit or availability for me, just on a very practical level of doing something, of trying out algorithms that vertex or that do event reconstruction or that may find hidden dark matter particles by a quantum computer disturbing entanglement and things like that. So this is really gone from just, okay, there's one or two qubits and you can use it, I don't know, to just code something up very small with Python and so on. And by now, really, you have well, in excess of 100 qubit on IBM Qs, and D-Wave is even more. There's lots of debate of what that means, of course, but still, I mean, this huge rise is to me that has changed even in these very few years, even 8 years, which isn't too much on this scale. What I think hasn't caught up, I guess, yet is our ability maybe to have the workforce, right? And to have students educated in how to use this in understanding fundamentals and yet also use it in the industry and make influential contributions, right? May that be to actually build these hardware platforms or also in terms of software like this, I think calls for some actions at university education systems and so on. And there is efforts, of course. I'm not saying there's none, but yeah, that's what I would say.
I fully agree with Andreas' vision. Indeed, I mean, for me, the most surprising thing is how fast it's really evolving. From the hardware part of view, we start, let's say, 5, 6 years ago with a few qubits, and nowadays we have 100, and really already we can implement or to simulate physical problem, relatively big physical problem in such a computer. While I mean, 5 years ago, really we can work just with a couple of qubits, and for me this is probably the most amazing thing in the field.
I've been trying to build bridges between CERN and high energy physics on one hand and AMO, so atomic molecular optic physics, for decades, not very successfully up to now. But it's allowed me the possibility of following what's going on in that field between, say, manipulating, controlling, using them in the last 20 years. 20 years ago, people were talking about laser cooling. Now they're talking about throwing atoms around, entangled atoms within a three-dimensional lattice of thousands of atoms. So, like Kristin, for me, the real big difference has been the possibility of now seeing quantum systems, that they're actually visible from individual ions to Bose-Einstein condensates. And then, really, for me, the most interesting part for using them to probe fundamental physics.
So I can jump in here and say I think one of the things that's been really interesting to me is how um, business has changed the way that I think about the physics that I do. When I started my career, there weren't really very many companies that were dabbling in the quantum space. There was D-Wave is there, I think, early on, but it wasn't really seen as something that was ready to commercialize yet. And I've spent part of my career at one of these startups. I spent 2 years at INQ. About now 5 years ago is when I left. But seeing how the roadmaps and the goals of those companies are the same and yet at the same time a little bit different than the academic goals, and how those ecosystems have started to separate out separate goals for themselves, I think is one of the things that for me was very interesting and something I really wasn't expecting to learn in my career when I started out doing a PhD in something that looked to me at the time very, very researchy. Still is, but certainly we dress it up in things like the Quantum to Business conference going on this week in a lot of language that doesn't sound like the language that we, at least that I learned it in lectures as an undergraduate.
All right. Our next question is kind of related to how things have changed that you've seen through your career. As you yourself have transitioned like into this career, what challenges or obstacles have you faced, and what advice would you give to students or professionals that are looking to enter the field and makes kind of a similar shift?
I think that maybe connects a little to what Kristin was also saying in terms of it's a change of, right, there's different languages that people are using, and the other is also that business applications are are changing and are getting more into that, or are expanding their portfolio of what they can offer to this. And that was also to me very challenging to navigate, let's say, because we have these or had these luck of being awarded some of these small business transitional grants from DOE or DoD. But then to explain what really is the advantage today for something that sounds very exotic and can deliver actual results today is a very difficult. So you need to be very good at communicating what it is that you can deliver and not just do fundamental research, which of course I'm still driven by that, but that doesn't mean one cannot apply things and actually provide solutions. But yeah, I think there it really these challenges to bridge, because it's two different, right? There's engineering, material science, AMO people, which are very different from me. We use different slang, right? So these all is very tricky or difficult to navigate, to form teams that work together, right? When I talk to a IT person at Purdue, right, that designs these quantum algorithm, it's almost unbridgeable, right? I mean, they worry about problems that I don't worry about that. I just want to play, right? I want to apply it and see whether it works. I don't design the next best algorithm to solve XYZ. So, no.
Yeah. Yeah, from my point of view, the main problem is that really this is an interdisciplinary area that really is in between IT and physics, quantum physics. So really, if you have a physicist interested on this field, for sure, he should know about IT and vice versa. Sometimes I don't know which situation is better. I'm not sure. But the point is that sometimes I deliver talk to my IT colleagues, and really I start from, let's say, from scratch, comparing the quantum gate with logical gate, the possibility of having superposition, and really for them the language is really strange. So that means that I think that probably it's better to have a physicist and really with a good background on IT, because really probably this is the most complicated thing to really to understand really the what is behind this quantum world, because it's true that all the tool and all the techniques coming from IT, that probably is easier to be understood, but probably this problem of really mixing couple of areas, quite different areas, probably is the main difficulty.
I guess I need to concur. Obviously, finding the right language, finding the right way to talk about the landscape. And this is not just between different areas, like you were saying, Jose, between, say, physicists and IT. I see this even within physicists. If you talk to solid state physicists, they have a completely different way of looking at the world than particle physicists. And within particle physicists, we've got the high energy physicists and the low energy physicists who see things. Well, for example, in high energy physics, you'd see a dark matter candidate as being a particle, and low energy, you'll see it as being a wave. And you need to think of these things in at the same time. If you're thinking about using quantum sensors, you often think of tiny little things that are, say, atomic scale. Sometimes they're diamonds. They're macroscopic devices. They work at room temperature. And trying to understand how these different people think about their particular fields and how they relate to each other, that's really the biggest challenge. So in fact, that's one of our work packages inside the collaboration we're doing, is to try to set up something like primers, introductions, dictionaries, if you wish, to be able to find a common language to talk about these systems and see where we agree on the words, where we need to make clear definitions to differentiate between them, and then get communication going at that level.
So I can underscore what everybody else said, but maybe with a slightly different take on it. One thing that I really love about the work that I've been doing here at Livermore is how interdisciplinary the work is. And it's at a really deep level where I've been working on projects, for example, where we bring together people who have expertise in microwave photonics, something that I hadn't known was a field that existed before I came to Livermore. And they've been working on things like developing the next master oscillator for the National Ignition Facility, not thinking about how to apply those same techniques that they're using to recreate stars to controlling quantum mechanical systems, which are some of the lowest energy scales for research at Livermore. And so I have seen that one thing that is really challenging for many people is to actually realize the value that they bring to a collaboration and to see themselves as somebody who is bringing an important key piece. They're on the team for a reason. Quantum information science seems to be something that gets the reaction when I say it on the train or the plane, and, oh, you must be brilliant, and it closes down the conversation. And really, it's just one of the things that is needed in solving the problems that come about with building quantum sensors, building quantum computers, and we need a whole lot of people with a whole lot of different expertise. I don't want to pretend for a moment that I can make a high performance computer like El Capitan, which is one of the world-class computers that we have here at Livermore, to make it work. I don't have those skills, and I'm really glad I can be on a team with somebody who has those skills. And it's the communication that gets us there, and the ability to be curious and willing to explore the boundaries of our own knowledge with people who we trust to help us make sure we're navigating it and trying to work together to get something done that we couldn't do on our own.
I mean, if I just to second that, like this, usually it's nice to be in a comfort zone, right? If a student asks me a high energy physics question, what does top quark or Higgs boson do? Yeah, I can answer that at least on the experimental level, right? I can get half asleep, right? But if they ask me on this, what we do in this in quantum science and quantum technology, right? Well, I have to admit, okay, I do not know the answer, but maybe tomorrow I can answer that, right? But it's a very different, and this kind of being challenged, I like, or I appreciate very much about this. Yeah.
Well, we can move on to the next question unless there's any other comments. So the next one is about which application areas do you believe might deliver the first commercially significant breakthroughs, and why?
I will be very careful in answering that, and especially now that I even start, like these things are always very hard questions and even harder to answer, and usually tomorrow they are completely irrelevant and outdated, so I will not really, I'll speak to what I can at least somewhat answer. That is that we have had some success. We submitted a patent for this quantum machine learning to optimize supply chain, and it is improving the outcome by 25%. So that is what I can say, and I think the why it works is because it is a very small niche problem to begin with that we are trying to solve. That is not, let's say, worth the attention of very big industry because there exist solution and commercial packages to optimize these things. But if you get to a very small and very complex problem, then this can provide value, or as we have then seen, it actually works. So at least that's what I can say. So this is mostly on quantum machine learning, where also the noise might be helpful. There's a lot of articles around that we don't even want noise-free qubits and all of that discussion, that this might actually help in giving random noise to the machine learning and wiggling it around. So I think there's a lot to that. But if you really there, I can also only repeat what I guess other people might know. Cryptography, I think, is among the technologies that's probably already used or will be used even more in the future. That is easier to adopt than like large cluster quantum computing. That might be really challenging for a lot more years to come. And I leave it at that. No.
No, really, this is a very, very, very tough question.
Yes.
It's true that now, just not even in commercial application, just is in, let's say, a useful physics output. Really, still is complicated to really to extract information or to solve a physical problem that cannot be solved in a classical computer. That is essentially the situation, except in very, very particular cases. And from the commercial point of view, it's the same. It's every time that a new discovery or limit is reached, really is a very, very particular problem. Not really very useful. I mean, it's good to know that really you can't go farther than in a classical computer. But from a point of view, still the problem that can be solved in a quantum computer, not solvable in a classical one. Let's say that there are very, very few, if any, indeed.
With quantum sensors, it's a lot easier because they're so extremely sensitive that you can actually reach into areas that are not accessible currently. And there are three areas that right now are already being used. Andreas already mentioned cryptography, quantum cryptography, that actually works with superconducting nanowire single photon detectors that run at 1.5 micron wavelength. And these are already being used and heavily being used. There's also quantum dots where you can think of using them, or they're actually being used right now in solar cells, but where there are medical applications that people are starting to think about and that are also just around the corner. And then the most interesting to me is nitrogen vacancy sensors, which are very sensitive devices for measuring tiny magnetic fields or variation in magnetic fields, which are being used or being built right now into sensors to navigate in environments that are completely opaque, where you have no optical information, like, say, underwater, deep underwater, where all you need is a good map and you just follow the map, a magnetic map, very precisely. So these are things that are already in existence, and very soon, or practically existence, are measurements of using the same nitrogen vacancy sensors of magnetic fields inside the brain. So you get a novel way of looking at currents inside the brain, or observing the brain practically in real time. These are things that exist. I have no idea what will happen in 5 years' time or in 10 years' time. That's something I'd love to think about, but already this stuff is science fiction. It's amazing.
That's true.
I'd underscore that answer and say that quantum sensors in many cases are here now, and they just need to be taken from the demonstrations in some cases to something that we can actually play with in the kind of the world writ large. But I mean, sometimes we define quantum sensors as something that is novel and uses quantum mechanics because we already have things like lasers and NMR machines that if we took out that novel part of the definition that we usually use for things that we need to invest research dollars in, they would totally fill the definition of at least the quantum 1.0 sensors. And there I'm thinking about, there's a beautiful review of Modern Physics article on quantum sensors that I usually go back to for the definitions of different kinds of sensors, ones that use quantum properties and quantum entanglement and large entanglement of systems. When it comes to quantum algorithms and quantum computing, I think one of the things that quantum computing is actually already providing value with is as a challenge, because we have been unchallenged in the algorithms that we're using in many areas for a very long time. And I think Andreas got at this with his answer also, but with a very specific example from his own work. Um, if there's no challenge, if we think that, what we have is good enough, there's no way that we're going to be motivated to actually look and see if there's something that we could do more efficiently. And that is a place where just having a challenge of this new technology that's offering a different way of computing already can push us past the current state of the art. The other place that quantum computing is commercially valuable right now is in hype. I think we'll get to this in the next question, but getting that press release about using quantum something in your current financial derivatives planning actually can give a meaningful boost to a stock price. And so that actually already is a product, although maybe not the sort of product that we like to think about as quantum physicists.
You are muted, Megan.
I am, thank you. Our next question relates to this a little bit, where how do you navigate hype versus reality in these fields, especially when you're communicating with stakeholders or investors or the public?
Yeah, I can maybe say a few things, at least in terms of also this applied solutions again with a company where we also went to like startup competitions, for example, in the state of Indiana with this with these gains that we had seen. And what one needs to understand, yeah, similar to what Kristin said, as soon as you say quantum, right, this is certainly a very a high bar then, right? Everybody thinks these are all genius and this will solve every problem in the world, and they stop really let's say listening on the limitations, right? They just see that. Um, it is true. I mean, it is true though, and also very interesting. Most of the, I mean, it's a very different language, right? The most successful at these competitions were usually app software developments, right? That have the ability to reach 10 million users in an arbitrary short amount of time, because that creates a very big opportunity for any venture capitalist or for any investment. So if you really want to have long-term relationship in terms of investment, it is that is non-trivial, right? You have to build this with the users or with the potential customers that actually want to get something out of this. So it's very tricky, I would say, to navigate that. On communicating science, it's I mean, yeah, I guess we need to be a bit mindful, but then on the other end, what I've seen is I do a data mine class. So far, there's about 700, I think, undergrads over the last years that went through that. It's always like 60 to 70 students every semester. And the section on quantum algorithm, or where they get some basic problem and they can learn, right, is one of the highest interest, right? So it is interesting to the students, and rightfully so, right? It's a future area where we should also provide this as an opportunity and form our answer in terms of, okay, how do we educate them and how do we tell them that? That's doesn't, of course, take away the hype. There'll always be buzzwords, right? It used to be nanotubes or whatever in the older days, right? So now it's quantum information science and quantum computing. So, but we should still offer, of course, the education that is needed in order to harvest and materialize all these really exciting technologies, yeah, or use cases.
Mhm. Well, regarding communication with public, essentially about the possibilities of a quantum computer, as I said, essentially nowadays, I mean, everything is in his fancy, essentially. Really, still, you cannot compete with a classical computer. But on the other hand, it's true that really the amount of people that is already interested in the field, and that really is in your classroom, or a future physics student or IT student, really is really creating a community that in the future can become a possible customer of this cloud computer that can be used and pay for his use nowadays. But it is one should be clear about the possibilities. Nowadays, there is a very nice future, but there is still a lot of work to be done. Not only about hardware, because that will be solved, I'm sure, in the coming years. But still, we have to work a lot on the possible algorithm and really to find an application. Still, there is no really a killer application that for which really quantum computer it's really the solution.
Yeah, I guess in my case it's easier because I never have to deal with investors. So I'm not tempted to have to kill their hype. But I do talk with the general public and students, and there, for me, it's less the hype than the interest that I like to work with. And of course, for me, it's also easy because I can talk about existing quantum tech sensors that I can point to, and where one can ground speculation with what is out there, while at the same time giving them visions. I don't want to be a damn squib. I steer clear of quantum computing, talking about quantum computing, because I don't know enough about it, and that's probably where most of the hype is coming from. But leaving people with visions and getting them fascinated in the technology and in the science, that's really where I see the hype helping us.
Yeah, exactly. After all, right, we can drive our field if we get more, right? We need the young generation, right? I don't, okay, I
Exactly.
do
Yeah,
work,
yeah. No,
right? But very
bringing in
different.
young people through this
Yeah.
venue is really a great way to do it because it'll allow them to satisfy their curiosity about what quantum tech is all about, and then they learn about what we're doing, and then they see all these cool AMO things and particle physics measurements and exploring the universe, and all of a sudden they're hooked.
Yeah. Yeah.
I I will say something that was implicit in a lot of the answers, which is I also try to talk to the public about what I do, so that there is not only messages that are coming out from, the front office of whatever VC funded company, but also some voices from, uh, or more voices from scientists. When I'm talking to people either inside of Livermore or outside of Livermore, I try to arm people with some analogies that are, at least uh, with some idea of how limited they are, but simple analogies like saying, we know that in general, a high performance computer can simulate systems that are about 50 qubits. Maybe it's more like 55 or 60 now. But if you have somebody who's saying they've done something that they can't do otherwise with something that is 10 qubits, you have this grounding that you know you can fully simulate it. And so using a couple of these rules of thumb, the sorts of problems that tend to work really well with quantum computers are ones where there's a small data input, large computation, small data output. Captures a lot, doesn't capture everything. But by giving a couple of these rules of thumb, I hope to arm people with a little bit of their own sense of what is real and what is not real. And then I can apply that to a couple specific instances, in the way that I'm talking about the work that I do and the work that others that I work with, and trust are doing, where I think they're making real progress in bringing this shared vision into reality.
All right, if there's anything else to add, we can go to the next question if not. So what skills do you consider the most valuable for the next generation of quantum professionals? Just, beyond, the obvious ones in kind of quantum physics or, the kind of related fields in like math and computing and things. What are the skills that you would kind of recommend that the next generation really focus on?
That's also a difficult or a somewhat difficult nuanced answer. I mean, clearly there is, and I am not an experimental physicist that builds devices, right? So, but that needs a lot of skill on the material science side. So I'm not commenting on that. On this, I think that the best answer that I can provide is certainly the AI ML fluency. So students should be starting to be fluent on that. Not so much yet for the large scale quantum computing because it isn't quite there yet, right? That's exactly, but there is exciting applications. So for that, for sure. But then I think in general, may that be material sciences or for quantum sciences, also to deal with the hype or this whole application sphere, right? We need critical thinkers or students that are able to go through this, let's say, jungle of applications and overhype also in industries, right? That may lead to, of course, dead ends as startups. That's how it's supposed to be. You just weed out ideas that are commercially not viable. But all of that needs, let's say, the skilled people and education. Maybe I'm repeating myself, but that I think is what is most valuable. Critical thinkers who can differentiate really hype or really something overselling from really yeah the inventions and that we need for this to harvest.
Mm. Well, I think that first they will need for sure a solid background in quantum physics. This is quite obvious, but also we don't have to forget. Of course, you have some knowledge on IT, and probably you will need this soft skill in order to be able to talk with people from different fields. It's also true if you focus on the, let's say, theoretical nuclear physics or theoretical high energy physics. Okay, in that case, with this will be enough. In other cases, you are more interested in developing devices. For sure, you will need also a solid background in solid state.
I think it depends a bit on the technology readiness level that you want to work at. I mean, are you going to build something? Are you going to use something? This is going to be very different. And since I'm talking about sensors, I'll talk about building sensors. And for that, technical expertise in experimental physics, like lasers, vacuum, experiment control, readout, these are very basic things, but you have to master those. You obviously have to know also the technical skills of what is quantum mechanics and how you're going to interpret whatever you read out. But these technical hands-on skills, I worry a little bit that those may get lost in the drive to sort of abstract reality and deal with it at a higher level, where you only consider algorithms and some underlying magic that then does whatever it needs to do. I'm a great believer in soldering irons and screwdrivers.
I can underscore that a little bit and say I don't know how many times I've gone back to the article on Poundrever Hall locking in so many different contexts. I'm thinking of the one by Eric Black, but feedback loops and all of those really practical things about how you make an experiment work with analog electronics generally are ones that I have found invaluable personally. More broadly, though, for the generic advice, I just say I think of the field of quantum computing and quantum information science kind of like there's this proverb of an elephant where you can come at the elephant from all different directions and what you see looks very different. So the skills that we need in order to get be it a quantum sensor, a quantum computer, quantum networking, to get those things working are really diverse. And so, what I encourage individuals to do is to find their deep subject matter expertise and curiosity, not to necessarily try to be a generalist, to have understanding of the general, but to bring some set of specific skills, be they in fabrication, be they in algorithm design, be they in deep knowledge of some of the application fields. Because really, I understand that getting everything done is going to take a big team. And so being able to understand a role that you may play in that big team is, I think, that's where to bring that extra technical. There's a really great article. There's one that came out from APS a couple years ago in the IEEE journal about just doing a survey of all the different skills that at that time quantum computing companies and quantum information science companies were saying they wanted from individuals. And you see a real breadth from the humanities all through the technical skills. And I think about that when I think about an individual asking me for advice to try to understand where they are and give them advice that's relevant to them because there's so many needs. Just as somebody who's not doesn't see themselves as inside the technology development. That's not something that is always apparent. I'd also say that on a more soft skill, the ability to work with what feels like imperfect information is a really critical skill, because if you're working on the interface of your own knowledge and a lot of unknown for you, it can be very parallelizing to try to make progress. And having understanding, or at least trying to find a way to work in that environment, is something that is really critical to success.
I began a bit of an outlier on this question, since I'm not really working on quantum technology. But to young people who want to work on the relation of quantum mechanics and gravity, my advice is that unfortunately, you have to try to learn everything, because important insights could come from any area of physics. In fact, any area we've heard during today's panel, and many other areas we haven't heard about. So it's very eclectic. So you have to be wide open. And I must tell you, at my stage of life, I do realize that that gives the young people an advantage.
I can also maybe add, just to counter a little what maybe Michael said earlier, that, or not counter, but add on. That is absolutely true. That even in my time when I was a student, right, I didn't know how to use an oscilloscope because it wasn't really taught, right? That's the thing. It wasn't really taught. So you learn this when you go to an accelerator or to a detector, and then they tell you, well, just pick up the clock, right? Just pick up the trigger line out of the crate and whatnot. So you didn't know how to do this. So you had to learn. And I think that's still what was discussed earlier. That's still true, that many of these students will need these kind of basics, will need hands-on. Sure, software is great, and I can put an algorithm together and maybe magic solves it. But it's also true that right, you should run toys. You should verify that whatever you have done or what you think you are doing on the machine is actually happening and not some complete nonsense, right? So these things still remain this kind of toolbox. Yeah, I totally agree with that. So yeah.
Yeah, and actually, if I can pick up on both of you and Kristin's comments, what you really need is curiosity and willingness to jump in the cold water and just play, work it out, figure out how it works. With an oscilloscope, it means figuring out that you're not actually going to break anything if you plug in the cables, and even if it doesn't work right away, you will get it. If it means working with a quantum computer algorithm, if the algorithm is wrong, so what? You just try again and get it to work at a later time.
Also, it's good to have into account if really you are using quantum computing as an end, or simply as a tool to solve a complex problem. I mean, you can say the same about let's say classical computing. I mean, you can be interested in computing, or you can be interested in solving a particular problem. Nowadays, I think that this is a kind of mixture, because really you have to define the let's say you have to map your problem that can be solved on a classical computer into the quantum one. Because talking about my own experience, really at the beginning, for me, it was not clear what to extract, which kind of output I can extract. Because in my case, typically I have Hamiltonian, I diagonalize, I just obtain the eigenvalues, and that's all. But then in a quantum computer, it's not so. So really to change your way of thinking in order to extract the useful information. And this is also very, very, very important, the change in your mind.
All right, we are at the top of the hour, so I think we're gonna finish out with one more question, and then we have at least one question from the audience. So maybe more will come in at the end. But the last question we'll end here with is, what is one misconception about careers in quantum technology that you'd like to clarify for audience members considering entering this field?
My answer to that would be that despite all the hype, right, it is there. So that means you need to get the right, or yeah, it is a full industry, right? There's many possible paths for future careers, right? May that be in the sensing or on the computing side, or in actually pushing boundaries of building these quantum computers. But all of these are complete careers for decades to come that will likely not go away, right? These things will stay and will only further be pushed. So I think it's true that we haven't seen, I don't know, a company that solves a very big problem, or it solves every NP hard problem or things like that, or there's a quantum sensor that can sense whatever, an airplane half across the globe, or it can sense dark matter particles half across the universe, right? These things are not yet quite there. But then, yeah, the path towards it, I think that's the exciting route. And there's entire careers, also as academics, right? University calls are out there exactly for that, for very interdisciplinary scientists, not for the niche specific ones that we have seen in the past. Yeah.
Probably it's important to be clear about that. Really now quantum computer is not for solving any problem. I mean, even in the future will be useful for solving very specific problem. Probably will be the only way of solving such a problem. But really, you cannot think in quantum computing nowadays. And I think that in the future, as in a classical computer. That's so in this sense, if you are interested in quantum computer not as a tool but as an end, that should be just should be clear. If on the other hand, really you are interested in using it as an end, really probably you will need to be able to define the appropriate algorithm in order really to map your problem into the quantum computer.
My favorite misconception about quantum tech is that it's all quantum computing, and quantum sensing is already out there. And as the name says, quantum mechanic is a mechanic. It's like taking up a screwdriver, a wrench, uh, tool, anything that will actually get down to the nuts and bolts. But more generally, and I think what both of you pointing out, and we've been talking about a lot, is that it's not a one-trick pony. It's a very wide range of activities, and only part of it has to do with IT and with computing, and most of it has to do with other activities that go well beyond just the computing side of things. As challenging as computing is, there's much more out there. And the other one is that quantum computing is just around the corner, is going to change the world radically. I'm not sure, as you've also pointed out, that unless we find real problems that are only going to be solvable by quantum technology, that it will be the kind of shift that people imagine sometimes.
Mm. I agree with that. Yes. Yes.
Fully agree.
I think everybody captured the misconceptions I was going to talk about with careers, so maybe I'll just add one more thing there. No, it's fine. Which is that I don't know if we know what the careers are going to look like in 10 or 15 years. I expect things are going to change a lot because we're still learning a lot about this technology and how we hope to use it. And I mean, when I was first thinking about quantum computers, we were thinking of them as something that was sitting on its own, doing its own calculation. And now the way that I think about quantum computers, if I'm talking about quantum computers and not quantum sensing, is I'm thinking about them as sitting to the side of a high performance computer doing just a couple of the things that they do well, because I know that most of the workflow that's going to be going on in that computer is not something they'll do well. So that's a small example of a shift, but it's a really profound one for what a career looks like. And so I'd say to expect change.
All right, well, we can go into our questions from the audience. So the first one that we have here is, I'm curious about this idea that AI science, while you're navigating, is impacting your ability to understand and deal with quantum developments because you're not sure if the results are reliable. What is your opinion on this?
I can say what I may have answered before, that is at least, and again, this is limited to the extent what we said before, right? I only speak a little bit on these quantum algorithm applied cases for very niche solutions, but there it's especially important that you have actually a toy model, and you actually have to run even on your quantum computer, right? You have to do ensemble testing. There's no way around that, because you cannot. I mean, you can simulate, but then that's not actually the real hardware, right? That's the problem. You can even simulate with some noise model that's as realistic as it gets. The vendors usually never give the noise model out anyway, so you rely on them to actually do it for you. So this is really not great in terms of scientific scrutiny that we wanna apply as a scientist, right? So you have to develop your own methods to actually do this. And then that, I think, increases your trust level, let's say, in the solution that you have. And you can look still at hybrid methods or classical copies of that, and you should see differences, of course, but it should at least be as good. Otherwise, I mean, what's the point, right? So you can use that at least. But again, this is only true for very limited problems that you can map to a quantum computer. No.
Well, typically, the kind of problem that you can solve nowadays, I mean, even if the only option to solve the problem is a quantum computer, in order to know if it's reliable or not, typically you make a kind of scaling, and then you start from a small and then you start larging. And in that case, you can really make either with a classical computer or with a simulator in which really you can test that your algorithm is fine. So essentially you are fully sure that really everything is fine. So in this sense, really, the result that you get is fully reliable. And typically, also you have error bar. So in that case, I don't have any doubt about how good is the result.
I mean, at the end of the day, you have to establish the ground truth for whatever algorithm you're using, whether it's an AI-driven one or a quantum computing-driven one or an AI-driven quantum computing one. And it's a bit like the experiments. We have, for example, we're running an experiment that's machine learning driven right now, and it does the complete experiment control. It runs autonomously. We're now expanding to get AI to run the experiment for us to really get the results that we want as rapidly as possible. But those are AI optimizations. And at the end of the day, you still have to verify what it's doing. You have to confront it with reality, and it will be the reality, the ground truth that will tell you whether what it's doing is actually meaningful or correct. And we're lucky we have this arbiter. We can actually ask nature, and nature will say yes or no, or sometimes maybe.
I'll take the question a slightly different way, which is I see, I use AI sometimes to help me summarize the literature that's out there. I use it sometimes to help me understand what other people are talking about. And so often, a place where I am using AI and where I'm questioning what I'm getting back from AI is in something that's always been a struggle for me, which is in staying up to date with the literature and what everybody else is doing, because there's so many people now who are working in this field, and many people are putting out great results, but many people aren't. And so it does go back to these same ideas that I heard from all the other panelists, which is, needing to trust in my own understanding of how what I've worked on personally and the people who I trust, how they've been telling me about the way that the experiments and the theoretical developments that they've been making really are working, and applying that intuition to the articles that I'm getting summarized or the articles themselves, as I always have had to, but now there's just more volume.
Hmm.
Our next question from the audience is asking for recommendations for books and resources, particularly maybe for an undergraduate level, to become more acquainted with quantum physics and your fields in particular.
Ooh. I don't have a book next to me, but I mean, to start with quantum mechanics is I think that ChatGPT probably can answer, or even Google. Like any good quantum mechanics book will give you some foundations, and then of course anything after that are expert literature. I mean, maybe this we can do. Maybe we can collect from all of us some book suggestions, and you put it somewhere connected to this webinar, because I can't answer that on the fly. Like there's books for algorithms and for sensing, I'm sure, and for everything. So, but that's, or at least I cannot do that on the fly.
Yeah. No, really, I realized that nowadays, really, I was thinking in myself when I was in my during my degree, and then I faced for the first time quantum mechanics. Really, nowadays, using all these marvelous tools for programming in a quantum computer, really, this is a absolutely very good opportunity to learn and to teach quantum mechanics. Because really, sometimes you start thinking about quantum gate, and sometimes you don't understand, but at some moment you have to stop and to say, come on, this is simply quantum mechanics. But so that mean that you can learn at the same time something about quantum computer and at the same time about quantum mechanics. And really some concepts really can be explained very nicely with such a tool.
Yeah, within our collaboration, the DRD5 collaboration, which is trying to do detector R&D on quantum sensors, we actually realized this need for resources. And so we're trying to do two things. One is a collection of primers on different areas of quantum sensing, where we get, curated speakers to talk about, to give an introduction into their particular field, where you know that you can then trust that particular area and that particular expert as a starting point to go further and then understand what the real concepts are. And we're also trying to put together, those of you who are high-energy physicists will know the review of particle properties. There's the review, and then there's the sort of the educational part of it. And we would like to do something like the educational part, where one gives introductions written by experts, short, few 10 pages introductions into the different families or types of quantum sensors. And this is more of an evolving document that continuously gets updated, a bit like the review of particle properties.
I didn't even know that existed or that you are preparing something like this.
No,
So
we haven't talked about it yet. It's sort of on our to-do list.
okay.
It's been stalled for quite a while, but we're new. We just started a year ago, so that's my excuse.
Yeah, exactly the DRDs. No, but this is great. I think that's exactly yeah. It's such
And
a
the idea
wide
is,
field that
and the point is that this should also be relevant for practitioners, like people who are active in the field who are already more established. I call this an exit ramp from high energy physics, so that they can actually do something fun and interesting in the future.
Yes. Yeah. Yeah.
So less particular to background, but more to particular to what's going on at Livermore. I'll point folks to our externally facing quantum website, which is quantum.llnl.gov, where you can find a popular summary of the work that we're doing in the form of a external magazine that we put out as a laboratory. We did a focus on our quantum work in summer 2024. And you can find that article linked there, which is a great start of understanding sort of the breadth of the quantum information work going on at Livermore, including our sensing and computing portfolios.
Great. Yeah. We have one more from the audience, just quickly before we finish up here. So this will be the last one. What is the scope of work going on both in research and industry when it comes to QKD protocols and PQC algorithms? Do you see PQC algorithms being pushed for implementation in the near future?
That is an expert question, I would say. I'm not sure. I think this is for what is this? Quantum encryption, I think is what that stands for, but I'm not sure I'm the right person even to competently answer that one, I must admit.
My understanding was that some PQC algorithms were already in use in select messaging apps, but I am also not an expert here.
Yeah.
No, me neither.
So you picked a good question, I guess.
Maybe we should invite the questioner onto the panel.
Yeah. Currently, yes.
Well, great. Thank you so much to all of our panelists for a wonderful discussion. I think this was really great, and I think there's a lot of really great information and advice that the audience can take away. So if time didn't allow for your questions from the audience, Leo dropped some information in the chat. I think we'll also try to follow up on Andreas's solution to see if we can kind of compile resources once you have a little more time to kind of get that put together, and we can try to maybe put it with the recording. But yeah, thank you everybody for joining us today for this conversation. As a reminder, all of the Quantum Series webinars are at the APS YouTube channel. This one will be included there as well. Thank you so much to our panelists for your time, and thank you again.
Thanks.
Thank you.
Thank
you
you,
for having
Megan,
us.
for hosting.
Pleasure.